Welcome back. We are now on chapter 1, section 1.8, continuity. The limit of a function as x approaches a can often be found simply by calculating the value of the function at a. Functions with this property are called continuous. We will see that the mathematical definition of continuity corresponds closely with the meaning of the word continuity in everyday language. A continuous process is one that takes place gradually without interruption or abrupt change. Okay, what's the definition of continuity? A function f is continuous at a number a if limit x approaching a of fx is f at a. That is, this limit must exist and it must be equal to the value at a. Let us see how this actually makes sense. Definition 1 implicitly requires three things for f to be continuous at a. 1. F at a is defined. That is, a is in the domain of f. Limit x approaching a of fx exists. That means left hand limit, right hand limit agree to a value. And these two values, limit x approaching a of fx is equal to f of a. The definition says that f is continuous at a if fx approaches f of a as x approaches a. Thus, a continuous function f has the property that a small change in x produces only a small change in fx. Okay? Limit has to be equal to value of a, value at a. The change in fx can be kept as small as we please by keeping the change in x sufficiently small. This you will see when you see a picture. Okay? Or it's difficult to explain without a picture. Let's come to a picture and then we'll talk about it. If f is defined near a, that is, in other words, f is defined on an open interval containing a, except perhaps at a, we say that f is discontinuous at a if f is not continuous. Discontinuous means f is not continuous. Okay. Another way, f has a discontinuity at a. Physical phenomena are usually continuous. For example, the displacement or velocity of a vehicle varies continuously, as does a person's height. But these discontinuities do occur in such situations as electric currents. Okay? Geometrically, you can think of a function that is continuous at every number in an interval as a function whose graph has no break in it. The graph can be drawn without removing your pen from the paper. So finally, here is a picture. Let's see. Any point here, your graph looks continuous. Aha, there is a discontinuity. And then your graph is continuous. Aha, there is a discontinuity. Now your graph is continuous at all these points, but aha, there is a discontinuity. And now your graph is continuous and on all these points. So remember, I was saying something about f has the property that a small change in x produces only a small change in fx. Look, a point like this. A small change in x does not change much in y. Whereas here is 3. I am just below 3 or just above 3. There is a big change. Here, just before 5 and at 5, there is a big change. Then after 5, you see there is a big change between points near 5, add at 5. Here at 1, before 1 and after 1, it seems there isn't much change. But at 1, it's emptiness. There is a big change. That's what I was talking about. Fx, if you are continuous, then the change in fx can be kept as small as we please. That's what continuity requires. If you are not continuous, then there can be big changes. All right. Now let's look at this. There is a discontinuity at a equals 1 because the graph has a break there. What is the official reason? F at 1 is not defined. You want value to be defined. What about at 3? At 3 value is defined, but the limits disagree. Left hand limit is equal to the right hand limit, so limit does not exist. What's wrong with 5? The value exists, the limit also exists, but the limit does not agree with the value. So you see, either the value does not exist or here the limit does not exist. Here both exist but they don't agree. That's what makes them break. Okay. So that's what we have explained just now. Now, which of the following functions are discontinuous? X squared minus x minus 2 over x minus 2. Or piecewise defined, 1 over x squared for x naught 0 or 1. Here, x squared minus x minus 2 over x minus 2 for x naught 2 and 1 if x is 2. And this somehow did not print properly. Okay, let us see what this is. For a part, f at 2 is not defined, so f is discontinuous at 2. Okay, later we will see why it is continuous everywhere else. But at 2, you know that the denominator is 0 is not defined. Here, B part, B question was this one. 1 over x squared for x naught 0 and 1 for x is 0. What happens to the value? Well, at 0, the value is 1. So what about the limit at 0? Limit as x approaches 0? Well, you know this actually goes to some kind of infinity. You can draw a graph and check. Check for yourself graph of y equals 1 over x squared. It goes to infinity. So limit is not a real number. So value exists but limit is infinity. We are discontinuous. Here, this particular function, what happens when x approaches 2? Well, factor the top. That cancels this because x is approaching 2, it's not equal to. Now when you plug in x equals 2, you will get answer 3. Okay, but what's the value at 2? Let's go back to the definition. At 2, value is 1. Well, too bad. You wanted value to be 3. They don't agree, so f is not continuous. This is the greatest integer function. Greatest integer function, if you remember, is the step function, greatest integer function. It is discontinuous at every integer. It breaks at every integer. All right. These are the various graphs of the function we just saw. X squared minus x minus 2 over x minus 2. You simplify it, you get x plus 1. That's the graph you get, except at 2. At 2, it's undefined. So this is discontinuous at 2. 1 over x squared looks like this. And at 0, you could very well give it height 1, but it is still discontinuous. Here is x squared minus x minus 2 or x minus 2. Correct? With the whole there. At 2, you give it height 1. It is still discontinuous. This one is the integer function. It's a step function. We went over this in class. Okay. I'll stop here and continue on the lecture next video.